Alright, time for another DraftScience video presentation. Sort of a part 2 or continuing regarding the Feynman lecture. One of the 6 videos, I believe, or 6 hours worth of lectures he gave in the 60s of some kind. And describing the quantum mechanical ways and such. The rest of them were quite boring, actually, compared to this one. And, but anyway, so this is the best of them, and it's on the 2 slit experiment. So he's prefaced it with a bunch of, oh, it's all going to seem so wacky and so silly, and blah, 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 blah. So anyway, yes, at the time I'm making this, I just found out that I'm not getting my internet back for 4 more days. So Verizon, just the tiniest of changes to my account. I just was changing, you have to call in every now and then because they start, you get out of your package and then they start charging you obscene amounts for nothing. And so, I'm getting bare minimum internet and paying $65 or something. It's an insane price for the crap I was getting. And so every, once a year you have to go through this process, and they just, every time they screw something up, and it's just, so, I decided to change the name. The first name was wrong. So we'll fix that while we're at it, right? And so they fucked everything up. They're destroying the old account, creating a new account. Obviously, it would make sense to not kill the old account until the new account is active. The sort of logical thing. So it says right on the order, the 13th, and they cut off at the 8th. And then they say, we can't fix it. And it wipes out my phone. It wipes, I have no internet, for a week. So, I mean, what's the point of having all this fiber optic crap, having some sort of durability, it can survive a snowstorm? Well, what's the point if they're going to be worse than a snowstorm? If they're going to just fuck up even worse for no good reason at all, and then lie to you, and say, oh, we can't fix it. I mean, bullshit. There's a number on the box. I'm sure they have that number. They say they deleted the account. Yeah, right, a 40-year-old account, you just hit a delete button. I don't think so, Verizon. I think that's a fucking lie. So anyway, just fucking assholes. I mean, the world is being run in such a shit manner. I mean, this is kind of horseshit. Like I said, this is the ABCs of being in the internet business is you don't disconnect your 45-year perfectly always paid their bill customers. You don't just disconnect them willy the nilly. You fucking assholes. And, especially the customers who have put up with you, ripping them off for years. Fuck. Well, anyway. Just too silly. Just too silly. So anyway. Now we're going to do physics too silly. So Feynman, I think, at this point has just pointed out how nobody understands quantum mechanics. Of course they don't, because it's a religion, and it's a really stupid religion. I mean, there's not even a Holy Ghost. There's no Jesus. There's no God. It's just Mr. Random. I mean, it might as well be Gumby and Pokey. I mean, it's just the silliest of stories. Mr. Random is running the universe. Oh, isn't that special? No, it's pathetic. Silly, stupid, idiotic, irritating.
If you appreciate this and don't take the lecture too seriously, that you really have to understand in terms of some model what I'm going to describe. And just relax and enjoy it. I'm going to tell you what nature behaves like, and if you will simply admit...
Oh, I gotta turn up the volume. Oh, it's always something. So, what the fuck? Oh, increase volume. Thank you. Yes, that's what I'd like. Increase the volume. Yes, thank you. See if it did it.
That maybe she
No,
does...
this didn't do shit. Okay, so I gotta change the view. Sorry. I mean, it's just I don't want to sit there and pause the video just to do something this frickin' simple. Everything's just...
behave like this.
Okay, so if you just take it, when you don't take it too seriously, if you just relax, you'll love this silly story I'm going to tell, but it's all funny and ha ha ha. No, it's not funny. It's an insult to my intelligence. I mean, okay, the rest of the dupes fell for it and they're not insulted, but you're insulting my intelligence. I'm way too smart to be fooled by this bullshit. What the fuck? I mean, can something go right?
Before he wrote his paper, but after people read the paper, a lot of people kind of understood the theory of relativity in some way or other, but more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics. Now, if you appreciate this and don't take the lecture too seriously...
Right, it's physics, it's science, don't take it seriously. We don't bother with any of that either, so, just have fun with it. It's just a fun little story. Gumby Pokey, it's funny. We put magnets in their butts. It's really funny. Yeah.
You really have to understand in terms of some model what I'm going to describe.
Yeah, something rational. No, forget about that. Liquor yourself up, take some drugs, and you all sound so whoa-y. Whoa.
Just relax and enjoy it. I'm going to tell you what nature behaves like, and if you will simply admit...
So he just pointed out how it's irritating for somebody to tell you some preposterously silly story that they don't have much evidence for. It's all convoluted and none of it makes any sense and nothing fits together. That's irritating. That's not fun.
Admit that maybe she does behave like this.
I've made lots of money and I'm very prestigious and I have this great persononia that I'm creating. I'm selling books now and I could probably sell ties or something. Feynman ties with little drawings on them, stick figures and such. So it's working out fine for me. So just why do you want to rain on my parade with anything called reason and rational skepticism? Why? Don't apply any reasonable skills here, and don't sit there and apply any scrutiny to this horse shit I'm going to tell you.
You will find her a delightful, entrancing thing.
Yeah, right, sure. So again, there's nothing. It's I can't even. They argue that they have something like this beauty of equations and stuff. There's nothing beautiful about these equations. They're full of horseshit symbols that don't mean anything. It'll take you 5 weeks to figure out what that symbol over there is. That symbol, that's not really a thing. That's another whole equation, that's all kinds of sloppy shit. Nobody ever wants to do it. So just approximate it. Put in 0.5. It'll be fine.
So that's the way to look at the lecture, not to try to understand.
Yeah, God. You're just like, no, don't try to understand. Cause it's a mechanical universe. Like I said, I could play you the mechanical universe videos. Everything is falling into place, except for the stuff they're screwing up. Everything else, though, is falling right into the mechanical universe place. I mean, everything else is looking very, very solid. Like, wow, nature's really, really precise. Things happen for really precise reasons. It knows when there's one tiny electron too many. It counts every one of them. They all count. It appears not to have any fudge in it at all, except the crap they made up.
Well, you have to understand the English, of course. But in any sense, in terms of something else, don't keep saying to yourself, if you can possibly avoid it, but how can it be like that?
No, that's the rational thing that a scientist should be saying is, how can it be like that? That's just too silly. So as soon as they tell you the religious story or some other wacky UFO story or some other, conspiracy theory, the first thing your brain should say is, oh, come on. 500 million people have been lying about the flatness of the Earth? Oh, come on. It's a grand conspiracy. They don't think we can handle it. We can't handle the flat Earth truth. I mean, you might as well be saying that. You might as well just be saying, go along. It's okay. I'll show you a couple of distorted images that'll make flatness seem perfectly reasonable.
Because you'll get down a drain. You'll get down into a blind alley in which...
See, that's their attitude. We thought about it for 10 minutes. We couldn't come up with an answer that's rational. So don't even try, because you'll hurt yourself. I mean, that 10 minutes is terrible. It's just anguish over this 10 minutes I had to spend trying to come up with a rational explanation. Something that fit with the whole rest of all the rest of the physics. I mean, you have to think about things like, well, all the forces are moving the same speed. They all seem to be doing this push thing. That's what momentum is. That seems to be the form of energy is in this form of momentum. You got to just figure out, you can put it together.
Nobody has yet escaped. Nobody knows how it can be like that. So then just let me describe to you the behavior of electrons or of photons.
So he did it again, electrons and photons, talking like there's the same exact results, the same experiment. They're not the same experiments, not the same results, different patterns. They're patterns, but they're different patterns. So again, just trying to imply that this is all so simple and they have it all sewed up when they don't have anything sewed up and it ain't all that simple.
In their typical quantum mechanical way.
So again, it's not typical. It's atypical. It's what fringe light does. It's what the light that comes right off the surfaces of a mechanism. It's a small percentage of the light doing this weird quantum mechanical thing. And that's something that's easy to observe or easy to deduce just from the simple idea of the single slit versus the single impediment. You can see the difference in the pattern. Sort of illustrating that obviously the slit is the light, some of the light's going straight through, and that's why it's terribly, terribly bright in the center, and the fringes, are fading in comparison. Where the single impediment, you don't have any of those effects.
The way I'm going to do this is by a mixture of analogy and contrast. If I made a pure analogy, we would fail. So it must be by analogy and contrast.
So again, he said before that you can't compare it to something in the real world. You can't compare it to things we know. You can't do bit. Of course you can. So he's just going to do exactly that. He's going to compare it to things we know, except he's going to straw man those things. He's going to draw us a picture that really isn't the only picture. It isn't the only way you could describe the particle, and it's not the only way you could describe the function of waves. So he's just going to cheat both of those arguments to make some argument that nothing answers the question completely enough.
Things that you're familiar with. And so I make it, and by analogy and contrast, first to the behavior of particles, for which I will use bullets, and second to the behavior of waves, for which I will use, say, water waves or sound waves. So we begin.
So again, and it's this whole wave-particle duality would be another context would be just like all the forces are moving the same speed. It's the speed of force. Again, this idea of wave-particle. We know particles can wave, so we know they can do it. If they're in the right circumstance, they can look like a wave. Even something as unmedium-like, like bullets, I can create something that gives the illusion of a wave of bullets. Even though it's not a medium and I'm not moving things through a medium, I can arrange the bullets in such a way as they look like they're waving at you when they're completely not. But it's really hard to think of that wave that I particleized. That's a little more difficult. The wave that stays contained as a single unit in space. Oh, that doesn't make much sense.
First, to discuss in a particular, what I'm going to do is I'm going to invent a particular experiment and first tell how it would behave.
Well, it would, that's sort of the key word here, is that it is all just an invention. It isn't a description of anything real. It's a description of a synthetic thing that he's building, a monster to be, to horrify you. So he's just sitting here and gluing horns on the little bunny rabbit. He's not giving you the truth. He's giving you a monstrosity of bits of evidence, but they're not, it's not the right view for you to get it. It's like you could take a picture of inside the rabbit's ear and then show it to somebody. Rabbit. Is that being honest? Well, yes, it is a picture of a rabbit in the sense it's inside the rabbit's ears, but it's not really saying rabbit, is it?
What the situation would be in that experiment using particles, what you would expect to happen if the waves were involved, and then what happens when they're actually electrons or photons in the system.
So he says again, electrons or photons. I got to keep emphasizing this just because this is one of their biggest lies. okay, is to pretend that the two experiments are the same experiment when they're not conducted anything like each other. There's no resemblance. The simplicity of the photon experiment is nowhere in sight when they're doing the electron experiment.
And I will just take this one experiment which has been designed to contain all of the mystery of quantum mechanics, to put you up against the paradoxes and mysteries and peculiarities of nature 100%.
Right. And so all you really have to understand is that, you know, the idea is that if you think this is an obstacle course, right? So whether we're talking about a beam splitter, you know, all the things that are doing something interesting. So we know the beam splitter in the case of the interferometer creates a pattern. You know, all the things creating a pattern, really all it comes down to is the same thing, which is all you have to understand is you're running light through the medium of the interaction between two different substances, you know, atmosphere and an actual material substance, and that it has to travel through that surface. You know, and the same, you know, that surface causes all kinds of bizarre effects in terms of refraction of light and different things. So you know it's capable of messing things up. And it doesn't matter whether you're flying through it, you know, this way into the surface or right along the side of the surface. There's every probability that whatever the atoms are made out of, you're going through some periphery of them. You're not going through the material, you're going through whatever's lingering on the outside of the material, which would be electrons. And that electrons scatter light. And so you can explain the whole thing by just understanding you're scattering the light.
Any other situation in quantum mechanics, it turns out, can always be explained afterwards by saying, you're
right. See, so they all really involve this idea of deflecting the light, changing its direction. And there's always something material involved in that change of direction. And if you just understand that theme, then you can understand why there's materials that reflect light in some kind of different way, because you've messed with the material, you've changed the material, and it's causing this effect where the light is being deflected, scattered by electrons.
Remember the case of the experiment with the two holes? It's the same thing. And so I'm going to tell you about the experiment with the two holes.
So again, he describes it as the experiment with the two holes, which, you know, if you did it with holes, okay, you have a whole new pile, there's a whole pile of new geometry that's affecting you, because you really don't have the same kind of surfaces to cause a consistent effect all along a straight surface. There won't be the same amount of bending, so each surface is going to bend a little bit different. So now the math doesn't even work. And then you have two patterns, but see, if you really tried to do the two hole experiment, then you might even get the clue that the two holes are less than a millimeter apart, and that at a long distance, at meters away, you can't see that there's two holes. You just get 1 meter away and you won't even see that there's two holes. And from 6 meters away, you're certainly not going to see that there's two holes there anymore. And you might realize that why don't I see that is because you're just going to see both patterns from both holes exactly the same. They're not going to be one of them's over here and one of them's over here. They're going to be right on top of each other, and there's just going to be the tiniest of difference in how they align. But, you know, that truth totally ignored in this science lecture. You know, well, I should say science, quote unquote, lecture.
Which is the general mystery, does contain the general mystery. I am avoiding nothing. I am bearing nature in her most elegant and difficult form.
So again, it's just a distortion of nature, a perversion. It's so inaccurate, so poorly described here, yet the simplest, you can't, you know, it's such a simple experiment. So let me pre-draw it just to make it clear. Now, it's not so simple with electrons, so that's their big lie. But the photon experiment really is just, you know, that simple. You just create a whole, look, it's a single slit even. I could just draw it as the single slit because it actually does exactly the same thing in terms of creating the pattern. So you're just shining light Okay, and you're going to get, if it's a hole, you're going to get a bullseye pattern. Okay, that's what you're going to get. And the two patterns aren't going to be miles away from each other. Like I said, it's just the tiniest of difference. So if you're viewing something that's a foot across, you know, because you're viewing it at a distance to magnify it so you can see it, you won't be able to see. If you close one hole and open the other hole, it's going to look like it's exactly in the same place. You're not going to be able to see that, oh, one of them's way over here. No, one of them's not going to be way over here. It's not two patterns, you know, inches across a distance. No, it's 1 millimeter, less than a millimeter. I mean, it's a tiny, tiny difference. Tiny, 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 tiny difference in the overlap. So all of this is ignored. The basic facts are ignored so they can lie and tell this fake story about a fake reality. But you can't get any simpler. Shining light, it goes through the two things. Now, Young drew the centers here for his math, okay, to do this geometry, to figure out where there's destructive and constructive interference. That won't work. Okay, if you use that distance, the center of the opening, you use that distance, you won't ever get the right answer. You'll get wrong answer, wrong answer, wrong answer. And what really works for the double slit, see the single slit, it's here and here. This is the distance in the math, the distance from the surfaces. And if you use the single impediment, what's the distance in the math? The surfaces is the distance in the math. And if you want to get the double slit right, well, you have to use all four distances. So you have the distance between these two, you have the distance between these two, but you have the distance between these two, and you have the distance between these two, really. So you have to use both of those distances. You have to use the smallest distance and the largest distance to be able to detect the actual pattern, because the actual pattern is got these glaring extra pattern in them. There's two patterns, not just one pattern. Now, alright, should be back. So, continuing with the drawing and such.
They start with bullets. But all the experiments are going to be in the same general design, so I'll draw it this way. Suppose that we have some source of bullets, which just represents a source, which we call the source, and is in fact, in the case of bullets, a machine gun. Then we have a plate.
All right, so again, that's just because these photons have to be randomized. So that's sort of the joke of it, right? Is, you know, we're going to try to dissect the phenomenon, and it never really occurs to them to say, well, what if we do know where the photons are going? Like, what if we aimed them? Which they can probably do now with current technology. They could actually aim the photons at the surfaces or, you know, different places in the slit experiment and see what kind of results they get. But, you know, it doesn't even occur to them. So, and in the case of electrons, there is no random. They're not looking for random. So when they're doing the electron experiment, first it's, you know, 1,000 times smaller. So everything is inside of a vacuated tube, and so inside of a electron microscope, essentially. And they're aiming the electrons. They put them through a whole bunch of you know, magnetic electric fields to lens them, to, you know, focus them. So completely unlike a machine gun. So again, just pointing out how this is just so inaccurate and so unfair to the truth. And the truth is where you can reveal the fact that this is just a story they made up, and they're forcing the evidence to fit the story. They're not looking for the right answer. They're just trying to defend the wrong answer.
In front here with a hole in it for the bullets to come out of, and this plate, in the case of bullets, is armor plate.
So this you don't need in the modern era with laser beams. You don't need to bother with this aperture. And the purpose of it in the past was to take light from a candle or from a light bulb and force it to be somewhat coherent, straight. So by putting this hole and then going a long distance from the hole, you could sort of guarantee that all the photons were coming in as straight as possible. And that's the purpose of it. But again, with a laser beam, you don't need this.
Then a long distance from here, we have another plate.
So again, he doesn't explain why it's a long distance. It's a long distance because you're trying to force all the photons to be in the same plane, to be coherent or culminated, as they say.
I'm drawing only a short distance because I haven't got room on the blackboard for everything, but this distance is supposed to be much longer in proportion to the width. Please expand.
It's not just much longer, it's 1,000 times or more. Much more than that even. It's supposed to be a matter of feet, a meter, 2 meters. You want the further the better.
That's the small point. And it has 2 holes in it. That's the famous 2 holes, isn't it? I'm going to talk a lot.
So again, he could describe it with one. He could use one hole and explain how there's an interference pattern. And all the same kind of questions could be raised as to how the pattern is created. And the real point is you could evade all of these questions about whether it goes through the left hole or the right hole. All of those questions go away because that can't be what's happening anyway. When there's a single slit, you know that a single photon has to somehow break into 2 for no reason whatsoever. There's no holes that are causing there to be 2 waves. Somehow in the single slit, there's 2 waves without any mechanism to create 2. So that's why wave theory fails. It's because it's kind of obvious there aren't 2 waves.
About these holes, so I'll talk about this hole as number 1 hole and the other hole as number 2.
So it's so simple, right? Just so simple. And again, Newton had done all these experiments already. He already did the single impediment using a hair, and creating the pattern. He had already done, the single aperture. And so all he didn't do was, so he'd done the outside surfaces and he'd done the inside surfaces, and so this was already something known about back in Newton's time. So there was no big surprise when the 2 slits showed up. Woo! Some kind of new phenomenon. There's nothing new about it. And they just pretended, like where none of us knew that there was a thing called Newton's rings. Nobody knew about fringe patterns? Of course, you must have known about them. Newton described them. You're supposed to all be physicists and experts. You'd know that Newton already described fringes.
And I'm only drawing it in 2 dimensions. You can, if you wish to imagine these as round holes in 3 dimensions. But
yeah, so of course, if you did it with round holes, you get an entirely different pattern. And you'd have to recognize, certain obvious things would become apparent, that these 2 holes are so close to each other, could be a hair's distance from each other. That's how small the measurements are. And we're supposed to believe, that those little things create all of this difference. And in terms of the 2 patterns, the 2 holes creating a pattern in distinctly different places. It's like you thinking your headlights spread this way, and get further and further apart the further away you go. Somehow the headlights get further apart when, no, they don't. They get closer together, actually. They get so to the point where you can't see that there's 2 headlights anymore. They move so close to each other. So it's exactly the opposite, the truth, from the intuition he attempts to describe.
Just say this across them. And then again a long distance away, but we'll draw it relatively short distance because of the limitations of this blackboard. We have another screen here.
So that's the target. That could just be a piece of film. Could be done a lot of different ways, but because he forces this to be, some sort of androgynous description, both photons and electrons are supposed to be included in this description, it completely breaks, an accurate description, because he's describing 2 experiments that aren't the same at all. And so he's creating a 3rd experiment that's never really done. It's never done this way anymore. And it's only done this way for specific purposes. So when the average 2 slit experiment's done, it's not done this way. You don't create a target that moves across to pick up the photons. You just sit there and watch them hit the wall. And you see them with your own eyes. and he's broken that simplicity by creating this fake experiment that no one really performs.
Which is just a backstop of some sort, on which we can put in various places what I will call a detector. And we'll mark that detector. Which in the case of the bullet...
So in the case of when they're doing electron experiments, that detector means they're going to use something that fluoresces, a fluorescent screen, and then they're going to see the light created by the electrons hitting the fluorescent material. So it's going to be an electron will hit, and then it'll create photons, and you'll see the photons created by the electrons. So it's hardly a straightforward. In the case of the photons, yes, they can do the experiment where they can actually move either the experiment or move the photo detector and detect photons at different locations. But the only time they do that experiment is when they're doing single photon type experiments. So again, it's, if he just stuck with light, then he'd have to say, well, look, we shine the light creates the pattern on the wall. And, start with that simple truth.
It's a box of sand into which the bullets will be caught, and we can count them. That's the detector for bullets. I don't want to have to redraw the experiment each time, so I'll label everything in this way, and then we'll be able to catch on to situations for different cases. And also, I'm going to do experiments in which I count how many bullets come into this detector or box of sand when the box is here, or here, or here, or here. And to describe that, I'll measure the distance of the box from somewhere on here and call that X. And I talk about what happens when we change X.
All right, so he won't be doing any of that, so he changed his agenda a little. But the simple idea would be is that, yes, you're just going to check at different locations, and that's the same thing over time as just looking at the whole image. So I could take a camera and just take pictures, across, and then I could just tie the pictures together and make the scene.
It means only you move the doggone thing up and down. All right. Now, first, I would like to make a few modifications from real bullets into idealizations. The first is that the machine gun is very shaky and wobbly, and that the bullets go in various directions.
All right, so that's not true for electrons. So again, the whole point of the electron experiment, 90% of it, 78% of it, whatever, is just about controlling how the electrons go into the slits. So before they even get anywhere near a set of slits, they're already being controlled. And the slits, again, are 1,000 times smaller than in the photon example. So you're talking about things where you're talking about distances of less than a human hair. It's insanely small slits.
Just exactly straight on and bounce backward. And they can ricochet off the edges of the holes in these armor plates. And finally, well, let's say, for instance, that the bullets have all the same speed or energy if you want, but that's not very important. But the most important idealization in which it differs...
So, of course, that would be incredibly important in the idea of recognizing that what's a feature of photons. Well, it is the fact that it is the speed of light. It is a constant speed and a constant energy. And then what's the other character going in that seems important? It will change the pattern. Well, it's the frequency of the light. If I use red light, the pattern will be one place. If I use blue light, the pattern will be a different place. So clearly frequency is something to be affected by the effect. The effect of the experiment will change things differently based on the frequency of the light. So it's critically important. But it won't be talked about because he doesn't apply any frequency to the bullets. He just says bullets. No frequency. Frequency is not relevant. It's not included. Yet, in the mathematics and in analyzing the experiment, it's clear that frequency matters. You change the frequency, you change the outcome. And so there's no conversation about a photon possibly being a frequency of bullets. Just even three bullets at the same frequency, same period between them. And if that was what was going through the experiment, that was what you were receiving, then your analysis would be completely different. You might get the right answer and figure out that this is just a pattern. A photon is a pattern. And it's a really simple pattern. And so you can take the simple pattern comes in, you can break it, and you have a 50-50 chance of remaking it on the other side. solved.
Some real bullets is, I want these bullets to be absolutely indestructible, so that what we find in the box is not pieces of lead of some bullet that's broken half, but we get the whole bullet, please. So imagine indestructible bullets, or hard bullets and soft armor plate or something. And now the first thing that...
So, like I said, that if he thought the one step further and thought, well, what if it is a pattern? What if some of the bullets get through of the pattern and some of them don't? Some of the half the photon hits the wall, the other half gets through. Those halves that get through could add up to a pattern. They could remake a photon.
We will notice about bullets is that the things that arrive come in lumps. When the energy comes, it's all in one bullet full of bang. If you count the bullets, there's 1, 2, 3, 4 bullets. The things come in lumps. They're equal in size, we suppose, in this case. And when a thing comes into the box, it's either all in the box or it's not in the box.
So let's understand that this is going to a particle analogy. So the argument would be is that there's a thing we detect, which is a piece of electricity. We detect electricity, and we call the electricity a photon. We say that when something has been hit appropriately in the photon-like manner, it creates an electric current, and that's what we detect. So that's how we're detecting them with a photodetector. Now, when they're just hitting the surface, obviously we're just detecting with our eye. But to do single photon experiments, we can't use our eyes.
It comes in lumps. More. If I put up 2 boxes here, I never get 2 bullets in the boxes at the same time. Well, if the gun isn't going off too fast and I have enough time between, you see, slow down the gun so they go off very slowly. Bing, 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 bing. Then put the 2 things here and look very quickly in the 2 boxes.
So he's talking as if this exact experiment in this exact form has been done well, and it hasn't. So this is sort of arguing that you can shoot photons in this single kind of manner, when the way they do that is to put a screen in front of the light source to basically block it. And then they basically say, let's count how many photons we receive on the other side of the opaque screen. And what the opaque screen is really doing is creating a bunch of those little holes. The opaque screen is creating weak spots where some of the bullets can get through. Now, the whole pattern can't get through the photon, but pieces of the photon can. So you're just right back where you started again. You're just creating a whole bunch of circumstances where you're getting pieces of a photon from different locations that all end up with the same angle, converging in the same place, and just reconstruct the photon. But you're not really seeing a single photon that left an emitter and traveled to you. That's not what you're getting. You're getting photons that spread out, they get broken, you take some pieces, and the pieces end up reconstructing the frequency.
You'll never get 2 bullets at the same time in the 2 boxes, because the bullet is a single, identifiable lump. I call that characteristic of the object that it comes in lumps. So the first thing about bullets...
So the key thing is that the detecting devices are lump detectors. So does the stuff really come in lumps, or is it a fact that the only way you can detect it is if it's in these lumps? And the lumps would be with enough pieces with enough frequency, the right frequency, to cause a reaction in the electrons that creates the electricity that we actually detect. So we're detecting an electric current, and we're detecting the minimum amount of energy that it takes to make the electric current.
Is that they come in lumps. And now what I'm going to measure is how many bullets arrive here on the average in a long period of time. So you wait an hour and you count how many bullets are in the can, in the sand, and average that. Now, we call that, if you want, let's say we take a definite time like per hour and say the number of bullets that arrive per hour. And sometimes you could call that what's called the probability of arrival, because it just gives the chance.
Right. So again, it's nothing to do with the probability. It nothing to do with some chance thing. It just has to do with the fact that there's variables, and the fact is how close to the surface did the bullet travel. And if it travels close to the surface, it gets bent a lot. If it travels further from the surface, it gets bent a little. The pieces end up going to all kinds of places, and it's either in phase or out of phase. So he doesn't talk much about the phase part. But for a bullet analogy, phase is just as important as a wave analogy. Phase is the frequency. It doesn't have to be a wave to have a phase. Phase isn't something only waves have. Lots of different things have phase. The phases of the moon. Yeah.
Chance that a bullet pointing through this thing arrives in this particular box, at least it's proportional to the chance. One way to measure is to measure the average number of bullets that arrive over a period of time. Now, the number of bullets that arrive in this box here will vary as I vary x. And I'm going to make a graph here in which I plot horizontally the number of bullets that I get if I hold this thing here for an hour. And I'll get a curve that will probably look more or less like this.
All right, just preposterous. So again, the slits are less than a millimeter apart. The screen is 5-7 meters away. All right, it's a gigantic distance. It's basically enlarging an image, but the two dots, the two holes, don't get spread out. Just like headlights coming to you, when the headlights are far away, they don't spread out. They don't, shoot and make headlights on the screen that are really far apart. No, they stay the same distance apart. Okay, they don't get further apart. They're not pointing in a direction out this way. They're not slanted. So they're only going to be a millimeter apart at the target. So this would never be created. These two humps that are, a foot apart from each other on the screen would never happen. They would just be, the two lumps would be right on top of each other. Just a millimeter of difference between the two. So it's just gives completely the wrong impression that the two patterns are in two different locations in time and space, when they're right on top of each other.
Because when the box is behind one of these holes, it gets a lot of bullets. The ones that went through this hole, and otherwise it gets them that went through this hole. And if it's a little bit out of line.
So again, just because of this drawing, it makes it really easy to think, oh yeah, it shoots off in these funny angles. But again, that's the whole point of it being far away, is to straighten the lines. The whole point of him saying the hole is, the slits are far away, a long distance. The whole point of saying that was for this very purpose, to straighten the lines, to make it less possible for all this spreading to happen. And the only thing causing the spreading is, again, the surfaces. Those are the point sources for all the fringes. All the rest of the light went dead straight. The rest of the majority of the light is just a bright spot right here. That's it. That's where most of the light went. In that tiny 1 millimeter spot. I mean, I'm not even doing it accurately. It's such a tiny little spot. It's as big as his thumbnail. Is the size of the space where 90% of the light's going to end up.
And it doesn't get as many. They have to bounce a little off the edges of the hole. And so it disappears like this. And this is the number that we get in an hour when both holes are open. And I call that, by an abbreviation, N12, which merely means the number which arrive when hole number...
Okay, I guess I'll draw this just to be, so there's just no confusion. Alright, so he drew, this stupid drawing, right? And what he should have done is say, okay, let's say even if we conceded his argument, he should have drew it like this, and then drew the other one like this, and then pointed out that these two can't be on top of each other, so this would be light intensity, so that these two would fill in this part here. Okay, so that part gets filled in. But again, clearly this is wrong, because the two slits, the openings, All right, it's just at 1 millimeter here. This whole experiment is inside of 1 tiny millimeter of space. And the only difference in where the two patterns are going to show up is going to be 1 millimeter. So none of this happens. None of this two patterns over here thing. If it was just going to be a plain pattern like this, then it would be one of them would be right there and the other one would be right here. You know, that's what they would be. They'd be right on top of each other. And the truth is these are both single slit experiments right here. So we'd know that this isn't what they're doing anyway. If they're really, really tiny, like, you know, very, very small, just a couple of hairs thick, a hair thick, even then, okay, the pattern is going to, you know, you'll have a big central maxima. Oh, that's a little crooked. And then, you know, you'll have all these secondaries that would go off like this. Now, if you do the experiment where you open the slits kind of wide, so if you make this, you know, a 1/4 of a millimeter and a 1/4 of a millimeter here, you know, you might get 50 of these bars. And as I've explained in a previous video, this is really 2 nodes. So a node is this size. You know, the on-off size of an on and an off is a certain size. And this just ends up being a little more than 2 of them here. And the reason is because it really starts, there's really a node here, and then the next node here, and the next node here, and the next node here, and there's really a node here, and the next node's here, and the next node's here, and the next node's here. And this part's getting filled in by the light that goes through the slits. Okay, so it's really fooling you. It's really a bright here and a bright here, and the center is being filled by a fake bright. But I've been over this in other videos. So there is reasonable explanation, non-magical explanation. And they just talk as if you don't have a choice but to believe their silly story. You know, there's no way out. We must believe. And it's all premised again on just drawing it wrong. It really helps if you draw it wrong when you're trying to tell a story that's wrong.
Hole 1 and hole number 2 are both open. Looks like that, say. Now, I must insist that the number that we're plotting here doesn't come in lumps. You can have any size at once. For example, there can be 2.5 bullets in an hour. In spite of the fact that the bullets come in lumps, what I mean by 2.5 bullets in an hour is that if you run a long time, like 10 hours, you get 25 bullets. So it's on the average 2.5 bullets. The N can have any size. It doesn't have to be in lumps because it's an average. I'm sure you're all familiar with the joke about the fact that the average family in the United States seems to have 2.5 children. It doesn't mean that there's a half a child in any family whatever. The children come in lumps.
Anyway, yeah, it's all right. Yeah, no sense of humor. I guess there's nothing to say about that except, you know, again, the lumpiness is just the byproduct of the fact that a photon is a distinct thing. If it doesn't have the right frequency, you're not going to see it as what it is. Okay, it's like to see a piece of blue light, it has to be the right frequency. To see red, it has to be the right frequency. If it doesn't have that consistent frequency, you don't see it. And now it's just heat.
But nevertheless, when you take the average number per family, it can be any number whatsoever. And so this number N, which is the number that arrive in this container per hour on the average, need not be an integer. It can be a tenth, which would mean under those circumstances that you have to wait on the average 10 hours more or less per bullet. So what we measure then is the probability of arrival, which is a technical measure, the probability of arrival, which is a technical term really for the average number that arrive in a given length of time. And now finally, if we go to analyze this curve N12, we can interpret it very nicely.
So, you know, there's not much in here that's interesting. I mean, the word probability is interesting, but again, we're looking for the cause, and the cause isn't some probability. The cause is mechanical events. And the fact is if you understand that each one of these surfaces the photons are being broken, and they still contain their phase. So when they land on the surface, they have a 50-50 chance of reestablishing the phase they were in when they left. So half of the photons will land in a way where they're not compatible, and half will land where they are. Like a tail will land with a tail if they were pennies. And you're just basically saying now they're all going to be changed into heads or tails. If there was heads, it's now a tail. If it's a tail, it's a head. Well, it doesn't really matter. And the fact is that if this is constantly producing tails over here, and this one and the other one's producing tails, then they can land in places where they'll reconstruct the photon. They'll be tails, 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 the way they're supposed. With the way they started, then they were broken, and now you're just remaking them. So there is no destructive interference. There's just breaking photons and then remaking photons. So there's just reconstruction. There's no destructive. There's just reconstruction.
We can interpret it as the sum of two curves, which I will draw here. You see, that's why I need the blackboard, where I got several cases. So I draw two curves here. One which would represent what I call N1, the number which would come if hole number 2 is closed by another piece of armor plate in front, and so they all come through number 1. And N2 would be the number that comes through hole number 2 alone. So N1 is the number that comes through hole number 1 alone, and N2 is the number that comes through hole number 2 alone, those numbers being determined by closing the respective holes.
So again, it's still the wrong drawing, and it's just a recopy of this drawing, the first drawing, except now he's put the showing the real thing. But again, it doesn't happen this way. It doesn't. The light from the point sources are not spreading. The point sources are the sources where stuff is going in different angles and different directions, but the point sources themselves don't move through time and spread and widen. So the two patterns won't be projected as, again, two headlights don't spread.
And then we discover
If you had two laser beams and you put them 1 inch away from each other, and then you shoot them a mile away, the two laser beams will get big. Okay, they'll become much bigger dots, but they won't move apart from each other. You won't see 10 inches between them now if you shot them straight. They'll just be the same 1 inch. A mile away, there's still just an inch between them, the centers. And that's true of this experiment. So the two patterns won't be in different places. They'll be right on top of each other.
The important law, which is that the number that arrived with both holes open is the number that arrived by coming through number 1 hole plus the number that comes through number 2 hole. And this proposition, the fact that all you have to do is add these two together, I call nice, or no interference. That is, what you get from the two holes open is the same as you get by simply adding each hole separately. That's for bullets done. We're done with bullets.
So the catch is that the two holes independently are interfering, because the two holes are basically single slit experiments. And the fact is the two surfaces are breaking photons. And the entire fringe pattern, all the fringes, is going to be made from those 2 point sources. None of the light that goes through the middle is part of the fringe pattern. That's why the center bright is 90% of all the light. The fringes are a small percentage of the light, the small percentage that went near the surfaces. And all of that light that went near the surfaces is the light that got affected, and that happens with single slits. So that pattern, even though it looks like some kind of nothing the way he drew it, that pattern still isn't made out of photons that took the trip and made it successfully. It's already made out of photons that had to break. That's how you made the fringes in the single slit.
I begin again. This time with water waves. Here is standing some kind of a big mass of stuff which is being shaken up and down. This is a long line of barges or jetties with a gap in the water in between. Perhaps it's better to do it with ripples than it is to do it with big ocean waves that sound more sensible. Wiggle my finger up and down here, and I have a little piece of wood here, and ripples start out here, and then I've arranged in a tank to put boards in the way here, so that I have these two holes, and then I have this so-called detector, and then what I do with the detector, what the detector detects is how much the water is jiggling. For instance, I put a cork in the water and measure how it moves up and down, and what I'm going to measure, in fact, is the energy of the agitation of the cork, which is exactly proportional to the energy carried by the waves. Also, I forgot to say that this jiggling is made very regular and perfect, so that the waves are all of the same spacing from one another.
All right, well, that's important to people like Pirro, who think that you can do this experiment with unregular waves and therefore prove it's somehow diffraction and it's not the same cause to the effect. So you can fake it. Garbage in, garbage out, noise in, noise out. So at least Feynman's being clear that now these are nice straight waves, so you create nice round waves, and if you did that in water waves, the two slits don't produce any interference pattern. Water doesn't do the single slit experiment. If you do the single slit experiment in water, you won't get the same pattern. You won't get the pattern you'll get in light. So they don't match. All right. So it's another critical feature where what they draw isn't the reality.
And then I'll describe what we get under those circumstances. For that, I first remark, well, let's see. First, we can measure the energy of the cork, but then another thing is important for light, for water waves, water waves, is that the thing that we're measuring can have any size at all. We're measuring the intensity of the waves or the energy in the cork, and if the waves are very quiet, if the thumb over here is only jiggling a little bit, then there'll be very little motion of the cork, and so on. No matter how much it is, it's proportional. So, it can have any size. It doesn't come in lumps. It's not all there or nothing. And what we're going to measure is the intensity of the waves, which, to be precise if you want, is the energy generated by the waves at a point. And now what happens if we measure the intensity, which I'll draw on a third curve here, which I'll call I to remind you it's an intensity and not a number of particles of any kind, and I1, 2, when both holes are open.
Right, and you would argue that this whole intensity thing gets important in the sense that if you look at the pattern, there is no obvious huge difference between the intensity of, say, the third bar and the seventh bar and the 10th bar. So it doesn't seem to get overtly weaker dramatically. It doesn't fit what would happen with real waves, which is the stuff going the longer distances on the periphery are weaker waves. But anyway.
Is a curve that looks something like this.
Alright, so this is nothing like the double slit experiment. So this is probably a good enough point to just point out how inaccurate this all is, and how the truth just doesn't matter to these people, and they're terrible cheaters and whatnot. Okay. So I've been over this so many times, but the double slit, so first off, if we take a grating that has a whole bunch of slits in it, you can expect a pattern where it's very spread out. And these will go perfectly round, because you'll see the actual image of the laser beam. So there'll be a great deal of distance, 2 feet, 3 feet between these spots, big distance between them. And that's all you get is just spots. All right, and then the double slit creates a pattern. Now, the catch is that you can cheat the pattern, okay? But the traditional pattern, if these are regular size slits, that is, if this is bigger than 1/4 of a millimeter, and this is bigger than 1/4 of a millimeter, this opening, and this is bigger than 1/4 of a millimeter. This is what you can expect. You can expect, maybe 12 little nodes in the center, and then there'll be a break, nothing, and then you'll have 6 or 5, let's just say 4 is good enough, because you're really not seeing one. There's really 5 or 6. There's really 6, but you can't see the 6th one. So you might have 12 here, and then you'll have 6 here, 5 here, and 5 over here. And the 6th one is the one that's missing. And that really is telling you, now there's a node here, there's a node here, there's a node here, and there's a node here, and they're all 6 nodes. And that's really what it's telling you. But anyway, the pattern has a clear break in it. Okay, so these clear breaks are distinctive of the double slit experiment, and the math that works and the math that doesn't work. So the math that doesn't work is the Young experiment. The Young experiment had the waves coming out of here and here, the center of the wave in the opening. All right, that math fails every time. It will not get the right answer. Okay, so that's just absolute rubbish. Doesn't fit the math, doesn't fit anything. And the math that works all the time just counts the slits, the surfaces. So that's all you do. You just measure the surfaces. And you just take the shortest distance and the longest distance between surfaces. So if the slits are less wide than the opening, then you count the distance between the two surfaces here. But if the openings are the smallest surface, then that's one of your you just take this distance and use that as one of your distances. And then the biggest distance would be this slit to this slit, and that would be your other distance. And with those two distances, you can figure out exactly where the pattern is going to be with those two numbers. Now, the trick you can do to it is if you make the slits insanely small, like close to less than a wavelength of distance, really, really smaller than a human hair. If you make them really, really small, what you're essentially doing is making this surface and this surface the same. You're just killing the distinction between the two. So your largest distance, your smallest distance, right? Your largest distance and your smallest distance would be that, but it's so small that it can't create any difference. So the real difference in the distances would be these tiny, the difference between this line and that line is just the same, almost the same line. So you don't have any change. You don't have any variety in the positions of the sources. These sources are so close to each other that they might as well be the same source, is the point. So if I make the impediment really tiny, okay, and have big slits, or if I make the slits really tiny and have a big opening, then I can get a single slit pattern out of the double slit. I can just turn the double slit into a single slit pattern by just making either the slits really tiny or the single impediment very small. But if I do the experiment right, I'm going to get this pattern, this complex pattern. And that's the truth, and that's not what he draws. And he doesn't pay any attention to these kind of details, and these details give you the answer. They tell you why. They tell you how. They tell you why this is twice as large as these nodes. All of those questions are answered by understanding, okay, the real geometry. And the fact is, the whole thing just has to do with surfaces. All the action, all the fringes are created by photons that come from the surfaces. And, that's a huge giveaway, okay, that this isn't about no random stuff. In the sense of this isn't about every photon that goes through gets screwed up. This is just about the photons that travel near the surfaces.
Now, an interesting, complicated-looking curve, which ought to be symmetrical.
So he's drawing essentially a single slit pattern and doing it very poorly because he doesn't have the central maxima, which is supposed to be twice as big. He doesn't include that. And he certainly doesn't, he's not going to be including the double pattern. So he's not showing us the real pattern, not even close. And it's a really important difference between the two experiments, and fundamental to understanding it.
I didn't do too badly, actually. Very complicated looking curve. That is, if we put the thing in different places, we get a very, very different intensity, which varies.
So, and again, the intensity really won't look like that in the sense that the little bars of light will look quite even. The third one won't be much different than the fifth one, and the seventh one, and the 10th one. So it really won't look like this. If you charted it, it really wouldn't look like that.
Very rapidly in a peculiar manner. And you're probably all familiar with the reason for that. The reason is that the ripples, as they come out of here, have crests and troughs.
Right, so he did it right. There's the same old traditional notion. Like, here's the center of this slit, and that's where I'm going to draw the wave center. If you use that in the math, you'll get the wrong answer. That's not what's in the math. What's in the math is the distance of the edge. The surfaces is the distance of the distance between the surfaces is what's in the math. So it's just a lie to say this is about the wave centers. Not two waves anyway. Four waves, maybe, but you have to put them in these preposterous locations that don't make any sense at all, which really says waves aren't the answer. This isn't wave phenomenon. It's scatter, and all you're doing is reconstructing the phase. You have a 50-50 chance of putting the photons back in phase, the pieces.
Spreading from here. And they have crests and troughs spreading from here. Now, if we're at a place which, say, is exactly in between these two things.
So that's the other joke. In between those two things, again, if that single impediment was 3 hairs thick, in between those two things is still 3 hairs on your surface. So you have a pattern that might be this big. Is what happens inside of 3 hairs here in the middle have anything to do with anything? No, it can't possibly have anything to do with anything. That's obviously a false positive.
So that the two waves arrive at the same time.
But they really don't. Like I said, that's so it's inside of hairs, and if you really take the real distance from the distance of the surface, you'll realize that this distance is many wavelengths across, and that there's actually a whole bunch of pattern inside of the distance between these two surfaces at a distance. And so there's a if you saw the Newton's ring thing, the idea is that the rings not only go out, they also go in. So there's little tiny ones on the inside and big ones on the outside.
The crests will come on top of each other, and there'll be plenty of jiggling, which is the exact opposite of this curve. So I'll have to put, there should be another bump.
Right, and there, but in the double slit, it's not twice the size. But the truth is the envelope pattern is. I don't want to make this where you get your first nodes off are the ones that are missing, the little bars that are missing. Those create a central maxima that's twice as large as the other nodes, but the little bars are all the same size. Because the little bars are being controlled by the two outside surfaces, and the big envelope pattern is being created by the two inside surfaces. So if you just think of it that simply, the impediment in the middle, those two surfaces are creating the envelope pattern, and the two outside surfaces are creating the little bars.
We have a lot of jiggling right in dead center. On the other hand, if I were to move to some point here, since I'm further from hole 2 than hole 1, it takes a little longer for the waves to come from 2 than from 1.
So this is just a phase argument. So again, distance would change the phase. So, that's just the alignment. So you could do the same thing with bullets. I have bullets and I shoot them a distance apart. And I shoot them exactly the same timing. And so they're both, so I got 4 bullets moving. And then I change this line here. One set of the bullets I make hit something. So it's a little slowed down. So one side's going the regular speed, the other side hits something, gets slowed down a little bit. Now I can realign the phase. I can do this, or I can have it do this. If it does this, it's not going to be able to see this frequency and this frequency anymore. And if I do this, it's not quite right either. If I do this, well, then I've done something that's probably going to be 2 photons again. So it just matters on how they line up. But the phase, being out of phase or being in a phase, is a 50-50. You have a 50-50 chance of being close to being in phase or far from being in phase. So it's this, you have a 50-50 chance of remaking the photon. So every time you break a photon, there's a 50% chance you'll remake it.
One has a crest arriving. The crest hasn't quite reached there yet from 2. In fact, it's a trough from 2. So the water tries to move up and it tries to move down from the influences of the waves coming from the 2 holes. And the net result is it doesn't move at all, or practically not at all. And so we have these low bumps at that place. And then if you move still further over, you get enough delay that when a crest is here, this other crest is in fact one whole wave behind. So in fact, if the crest that is, 2 crests are coming on top of each other.
Right, so you just remake the photon, right? You just reestablish the right frequency.
But not the same crest, so to speak. The 4th crest from here and the 5th.
Right, now you could make the same argument if he'd done that to bullets, right? So if he gave bullets a pattern, if he said this is a photon, right? 3 bullets with the same distance between them, then he could have made the same argument. You could say, well, anything that breaks this, knocks one of the bullets out, does something, I can always have that replaced by some other piece of pattern that lost some other piece, right? So this one could lose the middle one, and the other photon could lose this one. And I could combine those 2 and I remake the photon. So, if he would have given particles a chance, he could explain the why phase is important with particles by giving the bullets a frequency. But he didn't do that.
Crest from there on top. So you get a big one again, then a small one, a big one, small one, depending upon the way the crests and troughs interfere, as we say. The word interference, again, is used in science in a funny way.
So he says it's in a funny way because he really doesn't believe it's interference. So this is the funny part. So he doesn't really believe the wave interference idea. So he was illustrating waves, but he doesn't think that's what photons are. And his argument is that as soon as the photon went into the slits, that somehow they gave their life to Jesus, and they became believers, and they're in now a superposition of every possible direction they could go in the universe. And it's like they got scattered in every single possible direction, and that somehow they will do this probability math and know, well, I already went there, so I have to go here this time, so the probabilities will match. And somehow all of that mathematics is done by the universe in some, with their computer. The universe has a computer and figures all that crap out. When the simple answer is no. The photons are broken by the surfaces, and the pieces are remade into new photons. And their direction has been changed by the process of hitting electrons. Simple answer. Simple mechanical answer that doesn't engage any woo engines.
Because we'll have what we call constructive interference. When they both interfere here, it makes it stronger. Well,
see, he's even mocking it in waves, in water waves, when it's the truth in water waves. I mean, like water waves, that really does happen. It's pressure plus pressure. So the pressure has to multiply. And so that's the thing, he's mocking it like, I don't like this much.
They call it interference anyway, but the very important thing is that I12 is not the same as I1 plus I2, and we say it shows interference. Yes, interference. That's the funny term we use, it. Constructive and destructive interference. I didn't mention what I1 and I2 look like, but we can find out by closing this, for instance, to find I1. The intention that you get here, if the hole is closed, is simply the wave from one hole for which there's no interference, and that's this curve. N1 is the same as I1 and the same.
So again, all of that's nonsense because they won't be in these different locations. They'll be exactly in the same location. And it is a fact that what you're doing when you're combining, you have two sources and you have two sources, you can make more. When you're taking parts, you can make more parts when both of them are open. You're squaring how many possibilities there are to make the pattern. So remaking the pattern is multiplied. Let's see how to say that. There's an increase in your probability when you add more sources. So that's really what you're saying. So the single slit is really the two-source experiment, and the single impediment is really the two-source experiment, and the double slit is really the four-source experiment. And having four sources means with each extra source you are squaring how the potential matches you're making. Your potential to reconstruct a photon is doubled.
Same way otherwise I2, and this curve is quite different than the sum of these two. As a matter of fact, the mathematics of this curve is rather an interesting one. What is true is this, that the height of the water when both holes are open is equal to the height that you would get from number 1 open plus the height that you get from number 2 open. Thus, if it's a trough, the height from 2 is negative and cancels out the height from 1. So you can represent it by talking about the height of the water. But it turns out that the intensity in any case, for instance, when both holes are open, is not the same as the height, but is proportional to the square of the height.
So that's also bullshit. Okay, so that doesn't happen in water. So we didn't make any distinction here. Water doesn't square the height of the water. The water just doubles. So when the two waves meet, a wave 1 inch high plus a wave 1 inch high makes a wave 2 inches high. It doesn't make a wave 4 inches high.
It's because of this fact that we're dealing with the squares that we get these very interesting curves. All right, now we erase the machinery and start over. This time we start with electrons. We have a filament here, tungsten plate, holes in the tungsten plate, and for a detector.
So again, doesn't happen. All right, this has nothing to do with the truth. So electrons, again, because of their whole de Broglie nonsense, electrons are perceived as if they have a frequency that would be like in the range of X-rays. So they have a tiny wavelength. So, the slits would be infinitesimally tiny, tiny things. You could do the electron experiment inside of the photon experiment. It's so tiny. Inside one of the slits for the photon experiment, you could build the whole electron experiment. That's how tiny it is. And they don't randomly shoot the electrons. They deliberately aim them. Go to a lot of trouble to aim them into. And then they receive them based on, again, no indirect contact, very indirect. Where they're converting the electrons back into photons and viewing the photons emitted by the electrons. So not at all like this bucket, none of the features of this experiment are consistent with the electron experiment. And the pattern, again, isn't very similar either in the sense that all the bars have exactly the same intensity.
Any electrical system was sufficiently sensitive to pick up the charge of an electron arriving with whatever energy the source had. Or if you would prefer, we could use photons. And
so he just keeps switching, pretending the two experiments are the same. This is the photon layout. This is not the electron layout. So just be clear on that. So yes, he should just talk about what photons do and quit pretending that electrons are the same as photons. Not the same thing. I mean, you can even understand that electrons are charged. And you can understand that how do I even put an electron through a tiny material slit? The slit has to be covered with electrons. Any material substance has to have electrons on its surface. So how are the electrons going to be neutral? There's no neutrality. They're going to be moved away from the surfaces by the charge.
Paper with a hole in it, 2 holes in another sheet of black paper. Paper isn't very good because the fibers don't make a sharp hole, so use something better.
Yeah, I could have said soot, or we use, some other kind of. But anyway, so it's just this rambling, imprecision. Let's not take it too seriously, and it's really important. The mechanics of the physical mechanics are extremely important, because any mistake you make in understanding what you're doing is critical. So it's just like understanding the interferometer. Well, if you don't know what a beam splitter is doing, if you don't understand that the beam splitter has a bunch of little holes in it, and that the light that goes through the beam splitter is going to be spread by those little holes, those surfaces, and the light that reflects off the mirrored part, it's not going to be spread. No, these are critical things, critical details, and it's all just wiped away by this straw man, by this fake man, this fake physics, where they're pretty much, using the liberty, they're taking the liberty to just generalize and make it simple for the dopey people, but this is how they teach it to each other. I mean, it isn't any better. They don't use any more precision when they're explaining this as an actual physics course. So it's just a lie to say, they tell the real physicists the truth. No, they don't. I've shown the lectures. They don't tell them any more of a truth than this garbage.
And here, for a detector, a photomultiplier that can detect the individual photons around. Now, what happens with either case, and I'll discuss only the electron case, the other case is exactly the same, the case with photons, is this. First, so what we receive in this electrical detector, with a sufficiently powerful amplifier behind it, are clicks. Click, 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 and so on, with the source here. Lumps.
All right, so that doesn't happen with electrons. Let's just be clear. That's not how they detect the electrons. The electrons, they really can't do the single electron thing very well at all. So that's just completely not true. Now, when they attempt it with photons, again, I already sort of described how there's a real problem in trying to create single photons, because you don't know whether the single photons you're creating were pieces of photon, and you're just reconstructing. And you'll reconstruct different photons in different locations depending on where you put your screen. You'll collect photons in different locations. So their sources are now what's the source of the light is now the ambiguous part.
Absolutely lumps. When the click comes, it's a certain size, and the size is the same. If you turn the source weaker, the clicks come further apart, but it's the same size click. You turn it up, they go quicker, and it jams the amplifier. So you have to turn it down enough that there aren't too many clicks for the machinery.
All right, so again, I just point out, this experiment has never really been done in any really good clinical way. So you can find bad versions of single photon experiments, but they're all bad versions, where there is no scrutiny about, I've used Veritasium as an example. He has the photomultiplier turned up so sensitive that it's picking up 7 error photons a second. That's way too many error photons to be able to take a long time to do the experiment. The whole idea of having single photons is to wait a long time. Now, there's talk of the experiment being done like in the 1800s, but there's no good evidence of it. There's no photographs of it. There's no anything left behind. Just talk. So it really is void of any hard evidence. So it's just sort of a fable. It's just a story they tell about the big fish that was caught, and they don't have any pictures of it. They don't really have any skeletons. They don't got any evidence of it. It's just a story told. Yeah. Man, it's crap. All right, take a little bit of a pause. Yeah, it should be back. Do some more.
That you're using to detect. Next, if you will to put up another detector here and listen to both of them, you never get 2 clicks at the same time, at least if the source is weak enough so that, because of the precision with which you measure the same time. If you cut down the intensity of the source so they come few and far between, they never come a click in both detectors.
So the whole idea is to eliminate the possibility that there's a photon in both slits at the same time. But again, that's not how the experiments have been done. By Veritasium, for example, turning the sensitivity up, it means he had to speed up the experiment, which made it more likely that there was actually photons on both surfaces at the same time. And I would argue theoretically, it's the only way this thing works is there has to be photons at both. You can't even make waves. You can't do anything. The experiment just doesn't work single photon at a time. You don't get any fringes. The fringes are in fact made out of activity that has to happen at the surfaces in the same phase time. That meaning if there isn't two photons in the experiment at the same time, they have to be close enough to the same time that their phase would be just a half of a nanometer of distance between them. Very quick.
That means that the thing which is coming comes in lumps. It has a definite size, and it only comes to one place at a time.
Okay, so let's understand it doesn't come to just one place. That's another whole argument about how photons land. And the fact is photons have very large polarization. Photons are big things by atomic standards. The polarization, the thickness, the width of a photon, or the height, or however you want to describe it, is thousands of atoms across, for visible light. 1,000 atoms anyway. 500 anyway. Big. You can't affect one single atom or one single electron. It has to be affecting, it's a pattern. And so what I would argue it's doing really is creating synthetic electricity in the sense that it's causing a disturbance. It hits one electron here in one atom. That electron sends a disturbance to the other atoms that travels at a speed, almost the speed of light, and then another piece of energy hits, and that pushes it even faster, and then another piece of energy hits and pushes it even faster. And that's what's causing the electricity that we detect, the clump. So the clump isn't a clump. The clump is an event, and the event has steps in it.
All right, so for electrons, or for photons, we'll just use it.
So he crosses out photons. So he writes electrons, then crosses and writes photons, and then crosses it out. Because he knows, I should probably be doing this. Because this is bullshit. Because these are different experiments.
And therefore, what we can do is the same thing as we did with the bullets. We measure how many come, we measure the probability of arrival. What we do is we hold the detector in a certain place. Actually, if we wanted to, although it's expensive, we could put detectors all over at the same time and make the whole curve simultaneously.
Or you could use photographic plates, or lots of different ways of doing it, yes. So, yes, it's not that complicated.
Suppose we put it in a certain place and we measure at the end of an hour how many electrons came, and we average it. By the way, if I put detectors all along the back here, when one comes, it comes into one, but not from others. It just one goes off, and the other goes off, and this goes off, and that one goes off, so on. Just like with bullets. And we measure then the probability of arrival of the electrons. And what do we get? The number of electrons that arrive. The same kind of an N12 as before. This is what we get for N12.
So he's expecting, but everybody didn't know what he was. Well, okay, so yeah. So he's still waiting. You're not reacting. You're not going, holy smokes.
N12 is this what we get with both holes open. And that's the phenomenon of nature. That she produces the curve, which is the same as you would get from an interference of waves. But she produces a curve for what? Not for the energy in a wave.
Right. So it could be the curve you would get if you gave bullets a frequency. But because he didn't give the bullets a frequency, he can't say, oh yes, bullets would do that too. Their phase could be reconstructed. So again, that's what's missing. So again, this isn't a very good way to describe the duality between wave and particle. Because again, he completely cheated the particle by giving it no frequency. and therefore giving it no capacity to reconstruct the phase. Anyway, this is as good a place as any to quit. Yeah, so we'll call it a video and move on to the next one, which is going to be a little more tedious because he just kind of re-emphasizes the same points over and over, and I will re-emphasize my points over and over. But that's apparently that's what it takes, because even though I have provided a very good explanation, there's a link to a video. What is a photon? It's in my playlist subjects, and it explains the right answer, the mechanical explanation for the pattern seen. And you don't need to believe all this wooey crud. You can understand it for what it is, which is like a lot of other phenomenon, it's just scatter at the source, so to speak. Okay, so yeah, this has been a DraftScience video presentation and such. Until the next time, and yeah, that's enough.